Hello everyone. This is the first part of the lecture video, includes 3 Doppler effects questions in 3 different situations. Question number 1 is the first situation when a sound source is at a stationary position while an observer moves. Like you are driving in a car and hearing a band playing on the sidewalk without moving. Second situation is when an observer is not moving the position while a sound source moves. Just like question number 2, we are waiting for a train and hear the train whistle as the train passes by. Lastly, both observer and sound source move at different velocities in the same direction. Question number 3 is an example question to find the frequency of an observer from a car when an ambulance approaches the car at a given siren frequency. Okay, let's get to the first question in detail. In question number 1, we are driving at 10 meters per second past a band that is playing on the sidewalk. As you pass the band that is not moving, the frequency of a note you hear changes by 40 Hz. If the speed of the sound at the relevant conditions is 345 meters per second, what is the frequency of the original note played by the band? First, let's write down the Doppler effect equation and see what values we can plug in with correct sign conventions. I labeled the variables in the formula so you can understand it better. The Doppler effects formula have unique sign conventions for different situations, but we are going to choose the sign that yield desired frequency changes. Before we determine the sign, let's simplify the formula first. In this case, Vs is 0 meter per second as the speed of the source band is not moving. So we can simplify the equation into V observed is equals to C plus minus V observer over C. We don't need to add or subtract anything because Vs was equals to 0. And we multiply the sound frequency. As you move towards the source of the sound, like number 1, you, in this case, the observer, hear a higher pitch of the sound wave due to higher frequency than the actual frequency of the sound. Now, looking at the Doppler equation on the numerator side, what would be the proper sign to put in to have higher observed frequency than the frequency of the sound? Is it positive or negative? I think it is a little more clear when I substitute the C and V observer values into the equation. Observed frequency is speed of the sound, 345 meter per second, plus minus speed of the observer, which is 10 meter per second, over 345 meter per second, times sound's frequency. Now, let me ask you again. We want to have higher observed frequency than the sound frequency. So we need to have a multiplier that is bigger than 1. So the speed of the observer should be added regardless of the direction the car is moving. This ensures that the observed frequency would be higher than the frequency of the sound wave. So we can rewrite the first situation into Doppler equation, situation 1 is C plus V observer over C times sound frequency. Similarly, we can do the same calculation with the car passing away from the van. In this situation, like number 2, we would hear a lower pitch of the sound as you move away from the source of the sound because of the lower frequency. This allows us to use the same sign conventions concept that we applied in first situation and write the equation number 2 that F observed 2 is equals to C minus V observer over C times sound frequency. Since the question gives the change in frequency as you pass the sound source, we can subtract two equations, number 1 and 2, to find the differences of the frequency observed. So 1 minus 2, that is F observed 1 minus F observed 2, that is equals to C plus V observed over C minus C minus V observed over C times sound's frequency. So they have a common denominator. We can simplify by subtracting those numerator values. That is 2 of the V observer over C times sound's frequency. The key note here is that when speed of source is not moving and the question gives the change in observed frequency, we can use this derived formula to find the original sound frequency by rearranging the formula. So after we rearrange it, we'll have change in observed frequency times speed of sound over 2 times speed of observer. And we can substitute the numbers in. 40 hertz, 345 meter per second over 2 times 10 meter per second, which will give you the frequency of 690 hertz.